Hello and welcome to the second part of 6.1, areas between curves. In the last lesson, we looked at finding the area between two curves where you had a top curve, f of x, and a bottom curve, g of x, and you had an upper and lower bound, x equals a and x equals b. So you had four lines essentially that you were using to find the area between those lines. You had a top curve and a bottom curve, and you had two vertical lines, a left vertical line and a right vertical line. We did top curve minus bottom curve with respect to x. And when we visualize what our areas looked like, we would have vertical rectangles with a width of delta x, which is represented by dx in our integral. The area underneath your top curve would be the integration of f of x. And then the area under your bottom curve was the integration of g of x. And to find the area between the two curves, we had to do the area under the top minus the area under the bottom. Or in other words, the integral of the top curve minus the bottom curve with respect to x. Today, we're going to be continuing on with this notion, but we're going to be looking at areas between left curves and right curves. We still have two straight lines as well, but these are now horizontal lines instead of vertical lines. Our rectangles, therefore, that we would be visualizing will be horizontal rectangles. So what those might look like is something like this. So in this case, the width of each of our rectangles is now delta y instead of, let's fix that, just make that a little prettier, delta y instead of delta x, which means when we integrate, we are going to integrate with respect to y. The area underneath the right curve is no longer an up and down area, it is now a left and right area. And so to find the area between two curves, we're now going to have the area underneath the right curve minus the area underneath the left curve, and this will give us the area between the two curves. We still have an upper and a lower bound, but these are now y values. All right, so we're going to still be integrating, but it is now right curve minus left curve, and our upper and lower bounds are now y values. And we will be integrating with respect to y. And that's because we're thinking of our rectangles as being horizontal instead of vertical. So in our picture, what that looks like is this is our right curve, literally the curve on the right-hand side. This is our left curve. A is still our lower bound, and B is still our upper bound. So let's try one. We want to find the area of the region enclosed by x equals y squared and y equals x plus 2 by integrating with respect to y. As soon as it says with respect to y, that means that inside of our integral we should have a dy. That means that these are going to be the y values of intersection because it didn't give us y values in the question. Okay. And that means that our two functions inside should be f of y and g of y. Our problem here is we don't know which one's which until we do some sort of visualization. This one is already in terms of y, but this one is not, so we need to rewrite this so that it is a function with respect to y. So let's picture what this thing looks like. We actually did this one last day. So this would be our x equals y squared function. And this would be our x equals y plus 2 function. Our area is this area in here. And since we've been told specifically to integrate with respect to y, we need to know our y values of intersection. That will give us our a and our b for our integration. And hopefully we recognize that the purple one is our right curve. which makes this f of y. And our blue one is our left curve, which makes this g of y. So before we start, let's find our places of intersection. So we have y squared equals y plus 2, or y squared minus y minus 2 equals 0. Factor this, and we should get y minus 2 and y plus 1 equals 0, which means y equals negative 1 or 2. These are our bounds for our integral. So now we know that the area is going to be the integral between negative 1 and 2 of the right curve, which is y plus 2, minus the left curve, which is y squared. Take the integral of this with respect to y. Horizontal rectangles is what we're picturing. So in other words, they would look something like this. Instead of vertical rectangles that we pictured last day, our vertical rectangles would have looked like this. So we're still filling in the same space that we had before. We're just looking at it from a different perspective. That's all. This is going to give us 1/2 y squared plus 2y minus 1/3 y cubed, evaluating from negative 1 to 2. Or in other words, I'm just going to move over because I have big writing here. 4 over 2 plus 4 minus 8 over 3 when we plug in 2. And 1 over 2 minus 2 plus 1 over 3 when we plug in negative 1. So we get 6 minus 8 over 3 minus 1/2 plus 2 minus 1 over 3, or 8 minus 9 over 3 minus 1/2, or 5 minus 1/2, which gives us 4.5, or 9 over 2, which is what we got last time. So the key points here when you are integrating with respect to y, you need an upper and lower bound of your integral, which should be y values of your intersection points, unless you were given y values in the question. You need to know which one is your right hand and which one is your left hand curve, and those curves need to be written with respect to y. In other words, you need to rearrange them to be x equals and plug those functions into your integral. Okay. All right, we're going to try another one. What we're going to do for this one is we're going to try it both ways. We should get the same answer. We're just going to be looking at it from different perspectives. So the first one, we're going to integrate with respect to x. This means that our bounds are going to be x values of intersection points, because we weren't given x values in the question to use. Okay. This means that we should have an f of x and a g of x. In other words, we should have y equals functions. And this means that we're going to be doing top minus bottom. So let's draw these. We have y equals x squared, and we have y equals 4. So our two functions are already as y equals functions. We're good with that. We're going to be doing top minus bottom. The top is y equals 4. The bottom is y equals x squared. We can tell that by looking at the picture. And our area is this area in here. And because we're doing with respect to x, we're essentially picturing vertical rectangles filling in this space. Okay. Now we need to know what these intersection points are. And so we can do that algebraically, or you might already know that in your head. We do y equals x squared and y equals 4. You have x squared equals 4 or x equals plus or minus 2. That means that when we integrate, our area should be from -2 to 2 of our top curve, which is 4, minus your bottom curve, which is x squared, integrating with respect to x. This is going to give us 4x minus 1/3 x cubed from -2 to 2. So we're going to have 8 minus 8 over 3 minus -8 plus 8 over 3, which gives us 16 minus 16 over 3, or 32 over 3. We're going to repeat this same thing, but just visualizing this in a different way. Right curve minus left curve, integrate with respect to y. Therefore, our upper and lower bounds are y values, and we need to think of these as horizontal rectangles. So instead of y equals x squared, we're going to need to rewrite this. Okay? So our area is still this same area in here. This time we're visualizing this as horizontal rectangles. This, which means I need a upper and lower bound that are y values. So my lower bound would be here. This is going to be our a. This would be our upper bound, which is our b. So hopefully we can notice that our upper bound in this case is y equals 4, and our lower bound is y equals 0. The next thing we have to figure out is what is our right curve and our left curve. So hopefully we can notice that this right here would be our right curve, and this right here would be our left curve. And the question is, well, what are the equations of these things? Well, if our first equation is y equals x squared, we're supposed to have these in terms of y, which means I should have x equals functions, right? So as soon as you see with respect to y, we know that our bounds are y values. We should have a right curve and left curve. Okay, these should be f of y and g of y, or in other words, written as x equals. So if I rewrite this as x equals, I get plus or minus root y equals x. Okay, so plus root y is one equation, and negative root y is our other equation. Well, if I think about this right-hand side is our positive root y, and this left-hand side is our negative root y. So our right-hand curve is the positive, and the left-hand curve is the negative. So I'm ready to set up my integral. So my area is going to be integral from 0 to 4. Those are my bounds. My right-hand curve is root y. My left-hand curve is negative root y. And I'm integrating with respect to y. So this is going to give me from 0 to 4 of 2 root y, or if you prefer to rewrite it, many people might do this right at the beginning, 2y to the 1/2 dy. If I integrate this, I get y to the 3 over 2. And in the front, I should have a 4 over 3 from 0 to 4. I'm running out of space here, so I'm just going to keep doing this to the side. So I get 4 over 3 times 4 to the 3 over 2 minus 0, which gives me 2 cubed, which is 8, times 4, which is 32 over 3, which is the same answer we had before, which is what we should have because it is the same area. We're just looking at it from a different perspective. So which method you use will partly depend on what the question asks you to use. If the question says with respect to x, you're doing the first method, vertical rectangles. Functions are y equals, your bounds are x values. If you're asked to integrate with respect to y, you're thinking of horizontal rectangles. You should have functions that are x equals, and your bounds should be y values. If the question doesn't say, take a look and see what kind of functions were you given. Were you given functions that were written as x equals, in which case doing with respect to y would be easier? Also visually, what's happening? Does it look like you have a top curve and a bottom curve, or does it look like you have a left curve and a right curve? Some functions will lend themselves to be easier with a specific method. If you aren't asked, take a look at what you've been given and choose the path of least resistance. That is all.